Dr. Prodanović, thank you so much for coming on the show.
Thank you so much for having me.
How are you doing today?
Very good, actually.
Yeah.
It started a little hectic, but things are moving along today.
Yeah, it's been a little warmer these past, 2 weeks.
Oh, the weather is beautiful.
Yeah.
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 So, there was 3 days of rain, and I guess I've been in Austin for a long time. So whenever it's like rainy for like an extended period of time, I'm like, sunshine. I need my sunshine intake. Vitamin D.
Yeah, I feel that. It's so sunny here, especially like compared to like, or at least like Zagreb. Zagreb wasn't super sunny. I remember it was like sort of sunny, but like there were definitely a lot of cloudy days.
What's difficult? Zagreb is actually really nice. Zagreb being the capital of Croatia.
Yeah. Thank you for clarifying.
Which is where I'm from. But in November, it gets like 1 month of quite a bit of foggy weather.
Okay.
And it's difficult to take.
Yeah, I can see that. I can't imagine how people in like Scandinavia and Iceland and like Alaska deal with 12 hours or no, not even 12, like 24 hours of darkness in the winter.
Yes.
Yeah.
So when I visited Fairbanks back in the day, they would actually talk about it as they go for a sunny weekend. So they basically fly somewhere, especially when the winter gets a little long. So they just fly to California or something like that. They come back for like a sunny weekend. And I've heard people from Vancouver speak in the same terms. Like when it gets rainy, it's not that cold. It's not all that dark, but it gets rainy for extended periods of time, and they go for sunny weekends.
Yeah.
So hop on the plane, get your sunshine intake, go back.
I've never heard of that.
We should institute rainy weekends, like from Austin. Like
no, we should,
go for some rain. And I guess people who ski, they go for snow.
Snow weekend.
Snow time.
Yeah,
snow time. Yeah. Which is fairly easy. Colorado, but I don't ski, so.
Yeah, Colorado's close. Have I skied before? I skied when I was a really little kid. I remember that.
I never got into it. Like I was snow sledding big time because we would get so I'm originally from continental Croatia, which is close to Zagreb, about an hour away, and sledding was a thing. So especially we would get like 2 to 3 rounds of snow. And Zagreb does the same. And then as kids, we would just be out, like you come back from school and you're like out till 9 p.m. all cold and everything. But the thrill of sledding was a thing. But the hills were not big enough for skiing. Yeah. So I never learned to ski. Mm-hmm. And then as I moved to Texas. And
you're not going to find much skiing
I'm
here.
more into swimming. As a result.
So your hometown is Petrinja. I hope I pronounced that right. Okay, awesome.
That's a difficult one.
Yeah. So a connection that I made when I was reading up a little bit on your hometown, and there's 2 arguments for the origins of the name of Petrinja. Feel free to correct me if I'm wrong at any time, because you are the expert here in everything Croatian. But so there's an argument that it's from St. Peter, and then there's an argument that it's from the word Petra, from the Greek language, which means stone or rock.
Either is actually referring to the stone or rock.
It's really?
Also very common. So Peter is also. It's all originally from Petros, or Petra in Latin, and Petros in Greek. Okay. So it's kind of the same word in both Latin and Greek, and they were both influences. As you saw in Croatia, we are at the merger of those 2 influences throughout history. So yes, it's always referring to, but it's also biblical meaning because of Peter.
Gotcha.
And it's a common name too. So my grandfather is Petar. My grandmother, his wife, is Petra. My sister is Petra. Wow. So there's a lot of, and I have another, that's on my father's side, and my sister is my sister. And then on my mother's side, I have an uncle also named Petar. So it's a very common name. The Peter local version is Petar.
Gotcha. Yeah, it's like John here,
Yeah.
Joseph here.
We have John. We have a lot of John, which is Josip. We have a lot of those too, but Petar is a common name.
Yeah, I found it very fitting that, so Petra in Greek means stone or rock, right? And you yourself have made a career out of studying fluid flow in rocks, which I don't know. I found that very, very fitting.
Yes, and I was debating. So we were in the naming children. We had a long study of how to name our children. I have 2 children. So we did the engineering thing, the spreadsheets and everything. And Petra was a contestant because I have a connection also. I have a deep connection to my grandmother specifically. Also, uncle, I have not met my paternal grandfather because he died in Second World War. But he's definitely a person I wish I met. So in that sense, it was a contender as a name. And then I got stuck on the fact that Petar, if I named my child Petar, that would be a struggle in the United States. And one of the first tenets we had is that the name should be easy in both English and Croatian. And it would also commonly went into some derivative of the name. And then we didn't go with Petar or Peter.
Yeah.
And Petrov is also a little bit, it's a stumble to pronounce. So we let it be.
Petar.
Because
Yeah.
So,
Yeah, the rolling of the R's super difficult for me.
So, yeah.
I think another connection that I made with the name of your hometown was that I started reading about the history, and at least from the Middle Ages, there have been a super wide array of conflicts that have gone through Petrina. I mean, in the Middle Ages, you had conflicts with the Hungarians, and then you had an Ottoman occupation. 16th, 17th century, you have liberation from the Ottomans, but now Austria comes through. And then 18th and 19th century, Napoleon's armies come through. And actually a cool fact that I learned.
And we still have living trees from that area.
That's what I was about to say. That was super cool, yeah.
We call them Lipa i Lirka. So Lipa is the linden trees.
Lipa.
So those are linden trees.
Linden trees,
and
okay.
Some of them are, they were planted by Napoleon troops.
Yeah. I'm curious, is that do people go and visit? Is there like a plaque there? Is it like
Yes, there are plaques. So there's something that is interesting to me in reference to history is that type of history is called good day in that area. So it's not all that special. And there's an attitude in Europe versus United States that is quite different. So yes, you have a lot of history. A lot of it there's a series of geopolitical conflicts. And if I just integrate what happened from the aforementioned the lives of my grandparents onto me, you integrate 20th century in Europe with all of its conflicts. And I think there is still a tendency to kind of ignore that too.
Yeah.
And maybe that's part of also trying to forget the painful parts of these conflicts. Because Petrinja actually has origin, it was the border town. So it was built, original town was built as I think originally a wooden town that was part of the defense structure. It was on a river. And that town got burned down over the time. But it was always a border town, whoever it belonged to, or it was fought over. And during the Austrian time, it was the time of this, it's called Vojna Krajina, which is it was a military zone that is today's border between Croatia and Bosnia. And that military zone was established to defend against Turks. And one thing that we didn't actually get to, so close to, that's the actual town where I was born, Sisak, simply because it has a hospital, large hospital, that my town did not. So Sisak actually has 15th to 16th century town still standing that is actually beautiful to visit. Yeah. And one of the major victories against Turks at the time in 1593 was the battle at Sisak, which actually established that border. Otherwise, Turks would go way up. So, and maybe there would be a little bit more Turkish in Croatian language than there is right now. So, but that's, yeah, so there has been like always battles throughout. So I think there's a tendency in Europe to try to also kind of maybe forget about those.
Yeah.
And not to acknowledge them as much.
Yeah. I'm
just wondering about it philosophically.
Yeah. Philosophically, it's like there is a balance between, not, like you can't glorify violence, and I doubt it's good for the psyche of the people to dwell on something so horrific. Yeah. But then also lessons from history are lessons from history.
Yes.
Right.
Yes. So there's a balance there between the learning, but also guarding yourself from pain.
Yeah. But yeah, the connection I was seeing, I mean, even in the 20th and 21st centuries, you had World War II, World War I, fascism, and then the Croatian War of Independence from 1991
and my hometown was part of that too.
Yeah, so, very eventful from what I read.
And then the last thing was actually Mother Earth. There was an earthquake.
Yes, yeah, that's what I was about to mention.
So there's like this pounding that happens, and one part of me always ponders the resilience that you have to build from all of that pounding and rebuilding, constant rebuilding. Mm-hmm. So if you think about sort of building, that's actually a common economic term that is pondered in the United States, is like building family wealth, right? Or economic well-being comes from
generational wealth.
Building that over generations as opposed to restarting constantly. Mm-hmm. So basically, my grandfather's house doesn't exist anymore on one side of the family. On the other side of the family, it's actually in a town that was also from the last Civil War kind of, it was a smaller village, and that village is a consequence of the Civil War 91 to 95 is basically not inhabited anymore. There's only just a few people left. Yeah. So the houses still stand, but the value of those houses, nobody wants to live there. So that's my grandparents. Then my parents moved to Petrinja. Both of them just showed up in Petrinja. Mm-hmm. And that's where they met. And they both got teaching positions. So my dad was a teacher, what is equivalent? I don't know that there's an equivalent of a college that educates K1 through 4 teachers. Okay. We call it Educational Academy. Mm-hmm. So that academy just is producing teachers, and he was teaching at that college. And specifically in my hometown, there is that one. And there's actually a long tradition in Petrinja. Along with the military tradition, there's actually a teaching tradition, which is kind of an interesting, that also dates back to Austrian Empire. So there was, back at the beginning of 20th century, what is today's high school. Just a high school in town was a high school that was also educating teachers. Mm. And people would travel. Actually, my grandfather, who was not from that town, was studying there around 1909. My grandfather that I mentioned that died in the Second World War was born in 1890. I'm going to let you ponder that a little bit. It's a little scary, but he got married later because he was participating in the First World War. So kind of got married. I think he was 34, which is old for that.
Yeah, very old for that time.
Right?
Yeah.
So, and then my father also married late. Mm-hmm. And by the time I was born, my father was 48, which is kind of old for old times, I guess. Yeah. So then the family history spans basically 3 centuries. Crazy. But anyway, back to the components. So they met in my hometown and they built a house. You know, the standard, like we met, built a house, like it's the standard, let's build this and start this. And then the war, 91 to 95, the house remained standing, which is an odd chance in time of war, but it needed extensive rebuilding. And basically just before it was built in 1972 and just before the earthquake, we did major, or my sister did major renovations. You met my sister, Snježana. So major renovations, new roof, and then earthquake. And so every once in a while, you have this outside environmental, I call it environmental, pounding that just comes and wipes everything away. Yeah. Rebuild. And now, 3 years in, we got loans, figured it out, and it's rebuilt.
Yeah.
But then because you have to constantly stand in place and rebuild.
Yeah. That's
difficult.
That's why I thought the word Petroleum was so fitting, because
it better be a rock.
Yeah, the people there are resilient as rocks. Like through each tumultuous time, each horrific event, they stand firm and rebuild. And to me, that just seemed like a connection that I made in my mind that I had to tell you when I was reading. Yeah.
Yes, it's an interesting. I actually haven't thought about that way.
Yeah.
Yes, you have to. And then one part of me, though, especially in 2020, was like, okay, are we really? I moved out. Okay, my life is now here, so there's that. So I did choose different life, different path, and that's all great. But I went to my sister. I'm like, okay, tell me where you want to go. Let's go. Let's move. Like we'll help. We'll figure it out. Why are we still standing here and constantly getting bound? But she decided to stay, and that's where her heart is. Yeah. She's a doctor, and she really lives with the community, and that she doesn't. She also knows that if she leaves, the community will lose the only pediatrician. In the radius of some 25 kilometers.
Wow. How is the...
She doesn't want to do that.
Yeah.
So.
That's amazing that there's only one pediatrician.
It's a combination of both being somewhat rural community. So in there's a major draw to be in Zagreb or the major cities, but smaller communities are having difficulties having doctors. But that's true in Texas as well. Yeah,
that's right.
So there are different reasons and different kind of evolution, but that's true around here too.
Yeah.
Right? Yeah. So that's something she chooses, and I'm like, oh, okay, let's keep being a rock. Standing.
Maybe if the town ever considers a name change, maybe the attitude of the people might change.
Maybe. You never know.
But it's, it's maybe not such a bad thing to be as resilient as a rock,
No, definitely. No. Definitely not. And there is, if you actually think about it, that level of resilience needed for survival is way more common around the world than not.
Yeah. And a connection to the generational wealth you were talking about earlier is like maybe in the U.S., over generations, it's very peaceful and there's a lot of economic prosperity, so we can build generational wealth in families. But in Croatia, it may not be the same because of, how many conflicts and horrible events there have been. But you build up this like generational resilience, right?
Yeah. There's a balance there too. So I have those conversations with Skylar, my husband, in terms of us building things, because we are in the moment. Both of us are sort of like first generation wealth builders, if you will. So we're building things together, and we're consciously working on that, right? And one of my comments is that as we're kind of growing, I'm like, do we actually want to? Knowing that you have to learn to be self-reliant and resilient, honestly, no matter where. There's a little bit of luck or whatever, there's randomness. That's like, you didn't choose to be born as Jason Bott. I didn't choose to be born as Maša Prodanović. You're kind of planted in a spot and given certain circumstance. And there's a whole lot we don't. There's a whole lot we determine, mostly related to our attitude and resilience, but there's a whole lot we don't. Yeah. And people are pounded in various ways. Sometimes we tend to think about money, but sometimes it's health or situation at home, or like, and those can be regardless of money. They can be on the spectrum from very ugly to very pretty, right? Mm-hmm. So in that sense, you kind of don't determine that. You have to kind of go with that and make something out of it. Yeah. And I think there's one part of me I want my kids to be resilient. I don't want them actually to be. One part of me doesn't want to just give them stuff, right? And that's the balance I'm trying to strike. Because no matter what, their starting position will be way better, right? Yeah.
It's such a good lesson to learn that fortune, things left up to fate and kind of things that are out of our control or at least, so for some context, I'm a big Stoicism fan. Mm-hmm. And I love reading a lot of Stoic philosophers and things like that. And a big idea is that stuff that happens that's up to fate is neither good or bad, because everyone's given bad cards, everyone's given good cards in their hand, and maybe a bad card now might be a good card later, and a good card now could be a bad card later, right? Like, through your children being in a better spot than you were, that's a good card now, a great, amazing card. But down the line, you do have to worry about, are they going to be as resilient as I am, right?
And we all build certain level of complacency. When you're comfortable, you get comfortable, right?
Exactly, yeah.
So you have to find your ways to make yourself uncomfortable. A little bit of discomfort is a good thing. Mm-hmm. Where is the balance, and can you determine the balances? And you can't always.
Yeah. So. I think it's different for everybody,
Yeah. But I think it's also realistic, and I think also generational. I would never want to go to life of my. Every time I think like, oh, this is hard, and whatever comes along your way, look at the level of hard is like the number of proposals I have to write and things like those, like deadlines. Mm-hmm. And I sit down with myself and I was like, okay, Maša, get real. You think your life is hard? Think twice. Yeah. And one quick turnaround for me is like, compare yourself to your grandmothers. Yeah. Very easy one.
Mm-hmm. Yeah, there's someone in the world, this is a big idea that helps me a lot. There's someone in the world who is dealing with or has dealt with the exact same thing that you're doing or you're trying to deal with right now, but they had it worse, right?
Yes.
And they're doing fine. They got through it. Right. They're doing good,
And the danger of our time, as in 2024, is that there is all this imagery, especially online, that is typically catching people at their best time. And then it stays as some sort of permanent thing. And I don't reveal much of myself on Facebook or what have you. But what I do is relatively light, and there's a number of pretty images. You don't really see my hard times there, right? So then we all kind of tend to project an image. So all of these projected images tend to be way rosier than life actually is, right? And then it's extremely, if you're caught up especially online, you think like, oh my goodness, my life is so miserable. Look at all of these lives, how easy and pretty and beautiful and what have you they are. And I always, I try to limit online for my own children for that reason, because differentiating the two, it's kind of like it has to affect that same resilience in a really negative way, right?
Mm-hmm.
And I think that's one thing that we have to catch ourselves and correct. I don't want not to have everything that we can have because the online presence or general digitalization brings.
Yeah.
But we have to make sure that we kind of
Yeah.
normalize things the correct.
I mean, that's a fantastic point. Like even I don't know, in academia, right? Someone accepts an award and they go up and give a speech and everyone's clapping for them and they're on a pedestal. Like, you see all the validation they're getting from people, you see the praise, and you're like, oh man, they must be doing so amazing. But what you didn't see is like the sleepless nights that led up to that, or, you know, the trouble in their marriage because they were dedicating so much time to work and they couldn't connect with their partner. You know, like you even outside of social media, it's good to realize that like nothing is as rosy as you make it out to be, right?
And part of it to me is also like when I see like people who are, again, and it's a combination of talent and some of this randomness that kind of props some people way up, either in terms of recognition or money or this or that. So suddenly you're a billionaire or whatnot. And yes, there's a whole lot of work that goes into that. It's also kind of lonely.
Yeah.
And one part of me is like, no, it's okay. I'm all right. Like, I don't need to be all the way up there, because that peak is a pretty lonely place to be.
Mm-hmm.
And to me, relationships are, other people are very important.
Yeah. So I want to ask you some questions about your life, kind of going from being a high schooler to through grad school and to where you are now. And from what I understand about you, before your undergrad degree, you were more troubled by picking which career path to go down and less troubled by the actual difficulty of learning the material. From what
That's true. Yeah.
Because from what I understand, like you would have a history exam, electrical engineering, and you would ace both of them, but you weren't that excited by it, right?
True. So I have to say my elementary school was pretty demanding, given the history of my town. Now in retrospect, I'm like, oh, okay, that literature teacher I had was quite something, because I remember studying hard. I always loved reading, so that wasn't a problem. But like the grammar and the training, and there was some serious training going on even in elementary school. And I always enjoyed that. I was always a bit on the bookish side, and reading and studying was never an issue. But I learned early on that I like studying just for the sake of it, I guess, in school, because that was an achievement. But also, I know now, like, I like reading. My mom was a historian, or she was a history teacher, and I always aced history, no problem, because I would sit down and whatever was requested, I'd just learn. I don't like history per se, because a lot of it is just like really analyzing it, especially the way it's presented in schools. Like, here's a bunch of facts and years and wars or what have you, go list them. Putting in context is really found through literature. Like, how did actually people get by, right? Like, what did they feel, situation. So I like reading about certain times in history much more than I like just history on its own. So it's not some research that I like to do. But I did it anyway. My heart was in mostly math and physics and some chemistry. And that's where I really kind of really liked things. And I could just study on my own without being prompted to. But my second one was actually comparative literature, and I did actually think about it as a topic. It's my teachers in high school that said, because we would have these debates over something that was read and and I would engage a lot in those, and I would always, and one of the teachers said, okay, you're good in math, be practical. Go in that direction. So I did. But I did have excellent math and physics teachers that kind of ultimately. So yeah, it was never a question. I never worried, what am I going to study? Even though that actually the topic changed.
Yeah.
So I was very much engaged in math and physics competitions in high school because that was part of a big part of my high school. It's fifth high school, Peta Gimnazija in Zagreb. It was actually close to our game. I don't know if I ever...
Oh, really?
I pointed out the building a couple of times, but it's actually in that complex. It's one of the older schools. And it's one of the top it's kind of a college prep high school with math and science focus. Yeah. So that being the focus, I then also proceeded. I picked applied math as the topic. I love physics. I considered it strongly, but I'm very clumsy in the lab. I'm just a generally clumsy person, so that causes a lot of frustration when you're constantly spilling. And so I went more to the theoretical side of it. But to this day, I like applied math much more so than like abstract, entirely abstract, like algebra, number theory. That was never really I was more like a calculus to physics person. I need a reason, why am I doing this math? All of this math. So, and then I studied applied math. I really enjoyed my undergrad in Zagreb. And then I jumped over to graduate school in the United States. And petroleum engineering came rather late. I studied porous media, also somewhat serendipitously. Started studying porous media in graduate school because my advisor, when I approached my advisor, Brent Lindquist, for the topic, he was like, oh, I have this topic on porous media. And my answer was, what is a porous medium? It's funny, isn't it? So then at that time, X-ray technology was a new thing. And basically he was working with somebody who's doing experiments, which is enhanced oil recovery experiments in Berea sandstone. So basically doing water and oil displacement in a sandstone. And then following up with a polymer, which is one of the standard treatments in enhanced oil recovery, and then imaging all of that on a very small scale, micron scale. So that was completely kind of new, because at that time they figured out how to differentiate oil and water under X-ray. Normally density is too similar in order to properly distinguish in an image after reconstruction. And at the time, so they figured out, we can dope one of them with iodine or bromine and then differentiate. And I analyzed some of the first images from that. And that's how it started. So there's these opportunities that somewhat randomly come your way, and none of us know what they really are. Because those are the topics, especially in graduate school, they open at the time. And I remember him being super excited, like he was literally kind of jumping up and down. And I remember thinking to myself, why is this man so excited? I now know the retrospect, right? So now I understand. But I was like, okay, yeah, let's do that. That's interesting, right? Then you just go in that direction. One thing led to another. I arrived at the University of Texas as a postdoctoral researcher. So
I want to backtrack a little bit to the transition from being an undergrad in Zagreb to moving to Long Island, New York. having been to both places, I can say that they're fairly different.
Yeah.
And you have a cultural change and a language change. What were some of the feelings that you had when you started graduate school in a new place like that?
A lot of it I can now, hindsight is 2020, right? But it's like Alice in the Wonderland. First time you show up, there's a big shock. So first of all, in terms of motivation, I just wanted to go, go, go. I didn't know why. And this was in the environment, sort of, internet was just starting. I found my way. I was always big friends of libraries. And I found my way to the library of the U.S. Embassy and found the way how to get to graduate school. Started reading. You had to actually go find catalogs back in the day. Right? And there was some internet, like some pages on the internet, but it's not quite what it is today. Yeah. Right? So we're talking, I went to high school 95 to 90. No, that was college. So college was 95 to 99.
Yeah.
But I started looking at these things in high school. So before 95. And internet in 95 was really basic. Anyway, back then, finding the way how to do the tests. I had to travel. For one of the tests, I traveled to Ljubljana in Slovenia. Got on the train because there was not enough of them scheduled in Zagreb for me to get test results in time.
Yeah.
For one of them, I traveled to Vienna, which is not that far. It's 6 hours of train. It's not a big deal. But like when you think about it, and then you basically show up with 2 suitcases. I remember showing up at JFK airport, and it was flight that was arriving in the evening, 10 p.m. And I was like, okay, I can try to find my way to Stony Brook, which was 50 miles away. And I knew the trains and whatever connections. But then I'll arrive in the middle of the night to a place where I don't know. I actually didn't know that you could check out for 24 hours, that there's a call button in the dorms where I was checking in, because that was not something that exists in Zagreb. Yeah. Or it didn't exist then. Now it does. So I was like, I'm not going to now test my luck and show up somewhere at midnight, right? Plus, there's a certain level of safety. I don't know where I'm going. I might get lost, and then what? Right? Might get suddenly very expensive. I don't know what I don't know. So I'm going to sit at the terminal and wait for the morning train. So I go, and like this is Terminal 4, I believe. And I checked in my luggage because there was a place where you could check in my luggage. So I was sitting kind of snoozing at the terminal. And then they shut down the terminal, or they did in 2000 at midnight. And they said, you got to go out till 6 a.m. Okay. So I went outside, and I was sitting at the bus stop between midnight and 6 a.m. just watching business moving by.
Wow.
This is the little decisions that you make, and you roll with it. Honestly, it was fairly safe because it was quite busy, so you just sit at the bus stop entire night. And then I picked up my luggage and got on the train and got to Stony Brook. So when I arrived at the train station, there was a student there, and I asked for directions to the bus to Chapin Apartments. And the student there is a Chinese graduate student. And she's like, oh, you're new? Okay, come with me. And she was actually one of these residential hosts or people who... So she showed me where to go, and she's like, are you hungry? Come for dinner later. And okay. So I showed up for dinner to her apartment in the afternoon, and it was basically a whole bunch of students around the table, dinner, Chinese family style, everybody eating from... So first I was new to that. I've never been to a Chinese... I haven't eaten Chinese food until then because there was no Chinese restaurant at the time in Zagreb. So, and everybody was chattering and eating and sharing. And I remember just sitting there like, where am I? So, I'm laughing because I enjoyed those experiences so much. But part of it is like the style of food, the eating with the chopsticks. I was kind of knew about them, but it was like, and everybody was just chattering around me in Chinese, and I was like, this is hilarious. Where am I? It was also very, very, very warm at the same time, and I really learned to enjoy those moments.
Yeah. Was that your first time in the U.S.?
Yes.
Wow. What a night. That sounds crazy. Yeah.
Right. And then in the morning, you get situated.
Uh-huh.
And in the morning, they're just small things. In the morning, I showed up. I went to my department, and there was a very kind secretary there, and got through the offices for the paperwork. And then at the end of that, I said, "Excuse me, but where do I go to buy pillows?" Because that's like a one practical thing. What is the name of the store, right? To buy pillows, because that's something you don't know. It's like department stores are called differently. It's like, oh yes, Sears. Sent me to Sears. So I went to Sears and found some food. And then also trying out foods. I remember I'm picky eater. Remember how I complained about my firstborn that he's picky?
Yeah.
Oh, I was that person. So then in that time of 3 weeks of trying out foods, I essentially resorted to not eating much. As I was trying, like, do I like this yogurt? Do I like this cereal? Do I like this? Like, go on. So I remember kind of losing some good 10 to 15 pounds in the first 3 weeks until I found what I call like equilibrium of what am I going to eat when I go out, right? Because you have to try things out.
Yeah.
So.
I actually had a similar experience when we were in Croatia. I remember just like trying a bunch of different foods, and like I didn't always know where to get food.
Right.
So sometimes like regrettably I just wouldn't eat.
Right.
And then the next day, okay, here's where you get food. Oh, okay, cool.
Yeah. But that's fine. I'm actually comfortable, and I was comfortable with that at the time. I mean, I knew it was going to be adjustment, but there's all these small decisions that you kind of get over, and in your daily life right now, you just know, so you don't think about them.
Yeah, exactly.
And all of those small decisions, they kind of cause friction. But to me, that's also the exciting part. So I just take it as it is and move on. I didn't eat, big deal. I'm thinking now, maybe I should do that now and lose 10 to 15 pounds. Wouldn't be as easy, though. And now I'm comfortable eating pretty much everything.
Yeah,
So.
yeah. You've acclimated.
I acclimated to it.
Yeah.
My joke now is like, I eat food. Just whoever wants to feed me, please do so.
Your pickiness as an eater has changed.
Yes.
Yeah.
There are still things that I'm not going to eat, but like it has changed. And my attitude is like, if you're going to feed me, I'm going to just say, yes, thank you. Stuff
I
my
can
plate.
relate to that. Yeah.
Right.
So I'm curious as to any advice you would have for a student, researcher, or just person in general that's moving to a foreign country and is very displaced and is going through the same thing that you're going through, where you're trying to do new things and everything around you is really different. What advice do you think you would give?
So the simplest thing that you can do, some of it you have to understand that you have to go through the period of adjustment. It's also a way to grow. So now back to eating, if you ask me, I also, as an eater, was not very happy in a very meat-dominant food place. That's where I grew up. I actually tend to be more in the plant. And to this day, I don't eat as much meat. So my favorite foods are Indian, Mexican, with all of the flavor, and Vietnamese, like curries, and not so much meat. And if there is meat in it, it's cut up in, the texture is different. It's not just like one big chunk of meat in the plate. So that's honestly what it really is my first preference. Right? so you will find, be comfortable with the fact that like you will find in the process something that suits you as you better.
Yeah.
The second part is that the way to get over these things is to connect with people and understand them, and kind of like, I think the key is developing your empathy toward other people's experiences and look for connections, understand, like, so learn like where it is that people are coming from, what was their experience before. And one can do that ahead of traveling through reading. That's what all of the great masters, that's why they're great, because they can actually capture people really well.
Yeah.
So you learn those experiences and basically just find people are always there. There's somebody you can connect to. And it's kind of instantaneous, because you will, with people, you will click with some people. And so find those people you click with. That's it.
Mm. So I'm curious about the travel opportunities in petroleum engineering and engineering as a field. And from what I understand, Interpor 2024 is in China.
Yes.
Right? And you have your whole tour there in May.
Yes.
And then you went to, I know, a Norwegian conference last year.
Yes.
And I saw you at AGU.
Yes.
So to me, it seems like it's fair to say that you have a lot of travel opportunities.
Yes, and those are my work travel. I remember, so pandemic was a big shock for me because all of my travel stopped. And I was caught in the house with small children the entire time. It was an interesting experience. But 2019, for instance, I went to Saudi Arabia, China, Brazil, out of the countries, and Croatia. That I don't even mention. Right? And then the local, like, AGU in San Francisco, or was it in Washington at the time? I don't know anymore, 2019. But yeah, so there was a lot of trips. And then in addition to that, we do have determination to travel privately and as a family. So there's some additional trips that are not on the list.
Yeah.
And some national, some international, but we try to take as a family 2 to 3, sort of like a 5-day, which would be the vacation trips.
Yeah.
And then 2 to 3 weekends that is just us.
Gotcha. Yeah, I found it funny that Skylar went to San Francisco with you.
Oh, he's packing bags whenever I travel. Yes.
Yeah.
So and he went to, so in 2023 we went to Norway. And then we had the opportunity for my kids to stay with my family, which I'm immensely grateful for. But also our kids stay with his sister here in Austin when we go to San Francisco. And since his job is remote, we made the pact that we're going to try to do it as much as possible. It's a decision.
I'll never forget when we were, I forget the name of the castle that we went to, but he was in a Zoom meeting.
Stone.
Oh, Stone.
Stone.
That's fitting.
Yeah, S-T-O-N, which, hey,
Yeah.
talking about stones.
Talking about stones. But yeah, I'll never forget when he was on a Zoom call in a Croatian castle.
Right, that was bad.
like there was like tour guides behind him and like cannons from hundreds of years ago, and he's just
century.
Yeah, he's just here in a 15th century
that castle
castle.
was also part of the defense system against Turks. Yeah. Go back to our initial. Yeah.
Now it's the coolest Zoom background in the world.
Because he was like, what do? I don't want to cancel this. I work remotely. This is one sort of like meeting that I have to make.
Yeah.
I was like, all right. We do have Google Fi is pretty good in providing. Yeah, it's one of the best phones you can have for travel.
Yeah.
Otherwise, I'm not all that into Google this or that, but Google Fi is because wherever you show up, your phone just says, welcome to the country.
Oh man.
Give us a moment to connect you, and you
Yeah.
have free data. The data and maps and everything works just like everywhere else.
That's
and
amazing.
Calls are not that expensive either. Yes.
Yeah.
And you don't have to do anything. So when your phone welcomes you to Saudi Arabia, then you think about like, oh wow. Wait a second. So yeah, it's quite surreal.
Yeah. Yeah.
Though in Stone it gets confused, so sometimes it says that you're in Bosnia.
Yeah, it
as
is
opposed-
right on the
because
border,
it's right? On the
right?
border.
Yeah.
So it can get confused, plus minus 20 miles. And there it's like plus minus a mile.
Mm-hmm.
So yeah.
Yeah. Welcome to Bosnia. Welcome to Croatia. Welcome
Yeah.
to Bosnia.
So mine is sort of a kind of academic life.
Okay.
So there's a lot of academic conferences. Part of what you need to do to stay both in touch with other people doing research and to present your own. And I often also travel to teach short courses and things like those. So in that sense, like that's part of what you need to do. So it's part of life. That's on the research side. But if you were working in petroleum engineering or more broadly in engineering, a lot of companies are international. So you can choose travel.
Yeah.
And I think that you can, if that's what's important to you, you kind of state that as an intention. And then you look for work opportunities that take you in that direction.
Mm-hmm.
And it's not that hard if you're actually willing to do it. Right? Because depending on the different time, there were times in life that I couldn't travel much, right? But so because of that, if you're actually willing, it's going to happen. And you will kind of be attuned to opportunities that take you in that direction.
Mm-hmm. So, now for the juicy bits, I want to ask you some technical questions
all right.
about.
Life is not juicy enough. All right. Okay.
Maybe it's where my priorities are at right now. But I am super interested in your research, and I want to ask you questions about
Go
that.
ahead. I can watch out. I can talk about that even longer. So. Good news, we have a hard stop. So.
Yeah. So, I can name a few reasons why the study of fluid flow in porous media is so important. I mean, there's fossil fuel storage, fossil fuel extraction, groundwater usage, all of that. But I'm curious about your perspective on that question. Like, why is your research a field of research that is so important?
So I'm going to be fair and say there is a whole lot of important research.
Yeah.
Okay? Now, what motivates me, and that's personal, is that there is importance of energy, okay, in our society. And back to our discussion on integrating, 20th century or what have you, part of what I don't want to have about my grandmother's life is the lack of energy, right? And that's just the reality. So in that sense, there's sort of like society level importance. That would be the large scale. And yes, now we're in energy transition. It's ever more important. And yes, we do have to be concerned about climate. So we have to find the ways. At the same time, no technology changes overnight. No technology change is cheap. People just want things to happen and somehow, push a button. That's not how it works. We have to work out solutions, and often major technological changes can be scaled up typically over 10 to 20 years. Right? So yes, I'd like energy transition to happen almost immediately, but the reality is also, even in Texas, that is very well endowed in sun and wind, right? We can't have it reliably all the time. Mm-hmm. On a very, very windy day, it could be 60 to 65% of the energy provided, but I think there was ERCOT data from the last cold day we had. It was only at that time, don't quote me, 6 to 9%. And when it's very cold, yes,
Wow.
I'd like to have the heat on.
Yeah.
Most of us would. Right? So there is certain reality of transition that will happen. Now, that's the macro scale. So I like being motivated by important questions. At the same time, and I'm, again, personally not motivated by money. I'm not. There is money in petroleum engineering or energy business in general, but that's not that's not what drives me. Yeah. With the understanding that I do have enough, I meet the threshold.
Yeah, you have the bar to
so like
be
it's
secure.
not like
Yeah,
right.
yeah.
So there's certain security. Yes. Beyond that security, the rest is gravy, if you ask me. But back to then what kind of just excites me personally, I like fluid flow. And it is actually true that I'd be equally happy working in biomedical engineering, figuring out, blood flow around stents. I'd be okay with doing that too. So that's the part of the opportunities that opened to me with being at certain place and time in graduate school, for instance, right? And it was actually so right after I accepted the position at the University of Texas already, but there was actually the second one that I applied for that came as a possibility. This is why I mentioned blood around stents. It wasn't around stents. It was basically studying fluid flow around artificial valves in heart. Something I could be definitely excited to work on. Right?
Yeah, for sure.
And it's also, if you think about it, flow in a porous medium.
Oh, yeah.
Right. So in that sense, there is a lot of that. But in some other life, if my actually somewhere in high school, if my teachers or circumstances of whatever worked out in different way, I think, and especially with my family background, so my dad was a psychologist. He was in psychology and what's called pedagogy over there, like study of teaching or educational efforts. And my mother was in history. They were, as a family, they were really doing they were connected to people, so a lot of just community work. So I'd be actually happy in social work. I'd be happy in sociology. I'd be happy in comparative literature. So, and to me, that's all fine, right? It's just that life goes in a certain direction, and you take that path. So I'm personally I don't question it. I'm just happy with studying fluid flow. And on a certain level, that's just something that rhymes with me, and I can find then interesting problems to work on in a lot of areas. So I do tend to also do more fundamental research. That is a little less applied on the large scale. But that's just, again, a personal choice. And this is where I say that there's a lot of problems and aspects of problems that are important. I'm not saying that one is more important than the other, but one makes choices at the sort of intersection of the interest and what presents itself as an opportunity, right? And what's important to me personally, and there's space for all of that. In my opinion, there is space for everybody to find what they think.
Yeah.
I'm never going to be the person that what I do is the most. No, it's not the most important.
I really love how you don't overthink it too much. That's something that I myself could probably learn from, and probably other people can learn from as well. Like, you like fluid flow through porous media, and there's no XYZ reason why I want to do this. It's just, it's exciting. It's a fun problem for you. Right. And it's not deeper than that. But since it's fulfilling and you're excited about it, it makes you happy, then you can kind of and then you go down that path, and doors open up for you over time, and you just take the doors.
And you still go and read and find it, but you basically, with every opportunity that shows up, you kind of turn it around as like, is this for me? And if it's not, let it be. So yes, I have a certain level of comfort. It's like, it's going to be okay. Like, I don't have to chase everything. I have enough on my resume already without actually chasing all that much.
I'm curious about the security of having or storing fluids and gases underground. And just how can we rest easy at night knowing that what we put into the ground isn't going to leak up onto the surface?
I don't think we can ever rest easy at night.
Okay.
But
Spoiler alert
we shouldn't.
Yeah.
Right? We shouldn't. Right?
Okay.
So I'm comfortable being uncomfortable there. We don't have an easy, cheap solution for underground. So, for instance, if we move to hydrogen economy, this is again where Texas actually is in a pretty good position. If there is hydrogen storage, there is hydrogen storage in salt caves. So basically, caves mined in salt that are on the border of Texas-Louisiana border. And they're sort of like the size of them is about an Empire State Building that fits into one of those caves, and they're leached out. Okay? And that's, I don't know if, is cave a porous medium? We could get philosophical there. It's a big hole in the ground. Most of other porous media that we deal with in terms of storage are actually in rocks, and so they're reservoirs that are mostly in rocks, sometimes just sediments, but they're porous media that are much more confined. And that confinement essentially then determines how long will it take to draw from the reservoir. So in that sense, we don't have enough of those caves. So there has to be, and this is where technology takes a moment. There's geologists know about the salt. Salt is heavily studied. Actually, Bureau of Economic Geology here at the University of Texas is one of the places to go to learn about salt. There's an entire salt research group. Salt. And salt is this very interesting medium because it can be seen as a very, very, very viscous fluid because those bodies move underground and kind of flows in geologic time. But that also poses all kinds of technical challenges when you want to drill through salt and things like those. It's also very tight. So in itself is actually impermeable to leaks for the most part, unless there is some leaching. So it's an exciting thing to study. Now, if I have a cave, I can draw from the cave fairly quickly on demand. The second option is storage in former or depleted reservoirs. Why depleted oil reservoirs? Because we already know a lot about them. So when a reservoir is depleted, it was possibly shut down and not used anymore. We know where the access points are. We can revive them. We have 30 to 40 years of data, even if it's older data. So you know quite a bit. Because otherwise, the investment to learn is a lot of time and money. Just drilling one well, you know that's an expensive.
A very expensive.
Expensive thing. So now imagine if you're studying an area, you have to do first seismic survey, then drill a number of wells to actually get some access to the underground, and you're still sampling it.
And you still have
very sparse
essentially like a very minuscule amount of data.
Yes.
Even with drilling and seismic and things like that. Yeah.
So that's always the case, right? That's just the state of that's just what it is. It's just, subsurface, right? We just deal with that. So in that sense, like if I go to the reservoir, but if I inject now hydrogen or any gas, storage of CO2 is very relevant too. Is it going to leak? In reservoir, it's less likely because that place was a reservoir already. So now that I'm mentioning a reservoir, can I give you a little gift and something to play with as part of this discussion?
Yeah, for sure.
Let's discuss reservoirs. So I can have you make a reservoir. Stop. My favorite activity. So I'm gonna just supposedly guard this tablecloth, though if it leaks, we're in trouble.
Hey Luke, can the camera see this?
Yeah.
All good? Okay, awesome.
So I will ask you to, this is a very weird activity because we normally don't put oil into a reservoir, but that's what you're gonna do.
Okay.
So open up carefully.
Did not think I was getting into a science experiment today.
And then,
So this is the porous media.
yes. So what we have in
you
here
have-
is hydrogels.
Okay.
Often by brand name, they're known as Orbeez, though that's not what I purchased. I found an unknown whatever online and purchased a bunch, and then you hydrate them in water. But they start as basically like 1 millimeter across or so, maybe 1 to 2 millimeter per bead, and that bead hydrates. So these are polymers that kind of take all of the water in. So they're mostly water. And because of that, they're transparent in water. So this jar is full of hydrogel. So that's your porous medium. It's a packing of spheres. It's also a model of a sediment, right?
So for the
Very
audio
perfect
only,
sediment.
yeah,
sediment.
for the audio only people, there's a lot of clear.
There's a glass jar.
I'm gonna call them Orbeez because it seems like the
Yes.
easiest term for. So there's a clear Orbeez, and then at a certain line, it becomes transparent.
Because
And
it's
Dr. Prodanović
because I
is
added
explaining
water to it. Yeah.
because she added water to it. You can see through. That is super cool.
And then we're going to top it off with mineral oil.
So
Which-
now we're adding red
This is
oil.
mineral oil that we use in the lab in experiments.
Yeah.
I do have a lab. I'm not an experimentalist, but I do have one experimental student. And mineral oil is really what you purchase as baby oil. And it's the leftover of their oil refining. It's when all of the high energetic components are out of it. So now top it off.
Should I pour the
Yeah.
whole thing?
Just, we'll see,
Just a little bit.
as much as it takes.
Wow.
Okay, a little more if it takes, yes. Okay, okay. I think that's pretty good. Okay, so now we close the jar
Oh, here we go.
and close it really well. Okay, so now you have oil is on top. Why is it on top?
Density. It's less dense
So
than
that's
water.
what it does in subsurface as well. And there's also gas in here, air, that is. It's not natural gas, but
Are these the air bubbles here?
you still have a little bit of air on top.
Yeah.
You didn't fill it up all the way.
Oh, okay.
So that's your reservoir, and that's how it, over geologic time,
Yeah.
you will have, when oil is ready from where it was formed, cooked, cooked at the temperature and pressure that was high enough, then it becomes fluid and starts migrating. Now we're going to simulate that fast, very fast, because these grains are much larger than the reality. So just flip it over. Here's your oil migration through a porous medium.
That is super cool.
If you'd like, I have a
Yeah, so for audio only people,
you can play with it.
I flipped the container full of Orbeez over, and the red liquid is kind of making its way up to the top through the space between the Orbeez. But it's very slow, and it gets caught between the spaces. So you have this really cool... and because the Orbeez are clear, you can see through everything. And
Which normally you cannot. We
normally
deal
you
with rocks
cannot.
that
Yeah,
are-
yeah.
you need X-ray, right?
Yeah.
But it's hard to see this process. We can now see it with X-ray, but those are some very expensive toys. It's not your handheld jar.
Yeah.
And what was beautiful about this one, and he's watching another one, these Orbeez, and this is serendipitous, these Orbeez are basically a perfect size, about 10 millimeters across, maybe a little less. I measured them and I forgot the number, so number escapes me now. But the pore spaces they leave in between are perfect size so that capillary forces, so when I have two interfaces, I have water and oil interfaces in between, in the pore space in between these beads, right? Which I do in rocks and any kind of porous medium if I have multiple fluids. So there is the interfacial tension between the two. And essentially that there's that capillary pore force across the interface. So interface is curved. You can see curved interfaces.
Yeah.
Because it's basically, it's curvature times interfacial tension. Its mean curvature is equal to capillary pressure across. So those two different fluids can have different, so that fluid interface for fluids that don't mix can support difference in pressure.
Somewhat
and
following.
that difference in pressure is capillary pressure.
Gotcha.
And that's what when we are trying to push fluids through a porous medium, any capillary really, we have to overcome that. So basically, especially if I'm pushing the fluid that actually preferentially doesn't want to be there. Water wants preferentially to be around those, so it's called vetting fluid. And the oil is non-vetting, or gas is often non-vetting. Okay? So basically, you have to overcome capillary pressure to push things through. So for this oil to push through.
So vetting means water wants to sink down below.
Vetting means that water wants to kind of vet the surface of the solid.
Gotcha. So kind of surround everything.
And anytime I have two fluids in contact with a solid, one of them typically wants to be next to the solid. And that depends on the mineralogy of the surface. Okay? In this case, it's a bead that is already almost 98% water. So, of course, it likes water. And oil and water don't mix.
Yeah.
So then this bead likes water better, and it's water vetting. A lot of stones around are as well. If they're silica-based, especially if they're silica-based, sandstones are. A lot of stones around Texas are actually carbonate-based and they tend to be oil vet. But it depends also on the direct mineralogy on the top of the surface. So it's an exciting, actually, thing to study. So now, basically what I have is that buoyancy oil wants to go up or is moved by buoyant forces, right? And what's stopping it, and right now it's stopped, is capillary forces. And they get into, for this size of the bead, they get into the perfect equilibrium. And this thing can it will move a little bit, but they will get stuck, like over there as well, and sit like that for 2 weeks, 3 weeks until I move the jar.
Wow.
You can play with that. This is your Petroleum Engineering lava lamp.
Thank you.
And this is for taking it.
This is super cool. Yeah.
Anyway.
So this is what's happening in a reservoir.
Yes.
So you have buoyancy forces that want the...
That's why oil stratifies on top.
Right. Gotcha.
And you have that in a cup as well. It's just in a regular cup of water. If you pour some olive oil on it or something, what's going to happen is that it's going to immediately float on top because there's no porous medium to go through, right? So porous medium throws in a geometric constraint and solid balls.
And you add the capillary pressure,
and this is also why it's hard to flow fluids through porous media, because that kind of stops them in these small confinements. Of course, the smaller the confinement, harder it is to go through, or harder it is to get a certain volume through in time that you'd like. So now if I have, back to our discussion on hydrogen or storing any fluid underground, if I were to store CO2 simply because I'm taking it out of the atmosphere and sequestering it underground and I want it to stay there, then what I want is just that fluid to move through evenly and kind of go through a lot of space without preferentially just sitting in one spot and not the other, and then be stopped by a cap. And that's called cap rock. And in all reservoirs, we have cap rocks because otherwise I wouldn't have reservoirs to begin with, right? Something has to stop this. So basically, that's what happens in this jar. What's also beautiful about this jar, you can kind of shake it and recover all of your oil and get it all, float all of back to the top simply because you break it up in smaller bubbles. But that luxury you have in this handheld reservoir, that luxury we don't have in real reservoirs.
Yeah.
So essentially, what I want is possibly that CO2 to also get trapped like this and stay there for a long time. And if it does pile up, it piles up under the cap rock and sits there. Right? So, but that's for the CO2 that I want to stay there. If I want hydrogen, I actually want to take it out on demand. And then I have to, if I need it on demand, that has to be fast enough. And drawing it from a porous medium. So this is the difference of a salt cavern, which would be just this empty jar, right? And putting something in a salt cavern, then I can take it on demand much faster. Or otherwise, in a porous medium, I have to be comfortable with losing some. Some of it will. So hydrogen is a very small molecule. And it diffuses places where a larger molecule wouldn't, right? So we know already from some limited research that exists on the topic that it's diffusing, and it's diffusing laterally. So you also need much more lateral confinement unless you want to lose your hydrogen, right? So there's that. And the second part that is not there with CO2 is that various microorganisms like hydrogen a lot, feed on it. Now, if they start feeding on it, then they will grow in terms of like in form of biofilms. And if they do, A, some of the hydrogen is consumed, and B, whatever else is in there in the pore spaces will start blocking.
Yeah. And are they producing methane?
They could do that too.
Yeah.
So you have to then combine. So point is that you want to have their hydrogen then on demand, so you'd like to stay in that form. So this is where this interdisciplinarity of the research. We've studied microorganisms in reservoir. It's actually quite amazing that even at 3 kilometers of depth, you will find microorganisms.
Amazing.
And at some point, they're still studied. It's a little hard to say which direction will they go, but they were studied for the microbial enhanced oil recovery, MEOR, because you want microorganisms to actually produce surfactants that would reduce the interfacial tension between oil and water.
Surfactants. What is that?
Soap.
Soap
is a surfactant. So surfactant is a molecule that has a hydrophilic and hydrophobic head, and it basically latches itself in both, and that reduces the interfacial tension.
Yeah.
And then you can remove some of these blobs more easily. That's what soaps do.
Gotcha.
Dirt is organic.
So it's kind of like lubricant.
Dirt is organic.
Yeah.
So take it out with water. Right? So a lot of that study, for those of the listeners that are interested in chemistry, that is a very beautiful area to plug yourself into. Very exciting too.
Yeah.
And a lot of chemical engineers work on problems like that.
It really seems like an amazing symphony between chemistry, and I would imagine you need plenty of geophysical data.
Also rock mechanics.
Mechanics.
How do we geophysics, right? How are we going to learn about these materials? By sending waves through them. And they're very complex materials. So then interpreting those waves or whatever comes back is a problem. Right? And that's basically, we call that formation evaluation, but geophysics is a core scientific area that plugs into that.
And then I guess going back to the first episode with Dr. Perch, I mean, he's doing all the statistical modeling to try and predict.
That's the uncertainty.
What's the uncertainty? What are the values?
And that's in this jar. So every time you shake it, you get a different configuration of these fluids.
Yeah.
And the porous medium, like compared to rocks, this is really simple. This is a bunch of spheres all of equal size. We don't have that luxury in subsurface,
Yeah.
right? Have you done said rocks?
Not yet. No.
Not yet?
No.
Okay, it's coming. You're going to see the sizes of grains that compose a rock, if it's a sedimentary rock,
Yeah.
is large. Then you kind of put it together, and there's the genetic processes that fuse them together, change, squish, and so forth, right? I'm kind of using
Diagenesis, I think.
diagenesis is change, right? So those could be literally physical forces that reduce the volume and shape. They could be also reaction. There could be, then water is always moving through everything.
Yeah.
And just like water leaves little carbonates in Texas on your toilet bowl, so it does in between in between grains and fuses them together. So those are called cements. So typical original grain will have layers of cements that came over millions of years that actually create a rock in the end. It's fascinating.
That is fascinating.
And you study that with various versions of microscopy.
Yeah.
Scanning, electron microscopy, and so forth, that you can actually then look at all of those layers. And we can actually see the layers. Like, you can study as detailed as you want to. But at the end of the day, there's this bunch of scales that are in the process. At the end of the day, you're wondering, well, how is this wave going through all of these layers of different mineralogy, plus fluids, and giving me the signal that I need to interpret?
Gotcha. Yeah, it looks like, or it seems like to me, a chess game, but the board is different every single time you try to predict
shake
it, right?
this up, you're gonna get this. And again, this is the simplest of the medium that you could possibly have. And direction from where things are coming, how you might, it's all varying it.
So I'm curious as to, so if you had a layer in the, let's say, the top half of your reservoir that is more porous, so there's more space between the rock grains than the bottom half, what would that look like?
So there are different, so porosity is so porosity is just fraction of the void space. So there's no size to it. So what matters is both the how much of it, fraction, plus what is the size.
So if there's a lot of holes, it could have the same porosity as something with less holes but bigger holes.
Yes. Okay. So I could find spheres.
Yeah.
I could make these spheres twice smaller. And if I pack this jar with those spheres, and they're all the same, the porosity between two jars will be the same, away from the boundary effects that I have around the jar. Right? So, and that's roughly around 36%. We know that. We have a lot of those. So we've studied a lot of those. We've packed a lot of those. Let's say that it's 36 to 40%, no matter what you do.
And when you say percent, is that percent of the jar that's
Percent
open
of the
space?
jar that is open.
Gotcha.
The rest is the bead. Okay? So that's the close. So no matter what the size is, porosity is 36%. So in terms of content of how much I can store, I know porosity gives me what that is, right? Times the volume that I have of the reservoir. But the size tells me how fast I can do the process of withdrawing it.
So the flow speed is to size.
So that goes to that number we term as permeability.
Okay.
But basically, I'm looking at and if I'm looking at the flux through anything, tube as well. Tube we study really well. So if I'm looking at this tube, then the flux, basically in terms of R, radius. So permeability scales, which is just a geometric factor that we use in the law. The flux will actually scale with R to the 4.
Wow.
Okay. Yeah. So now if I divide my R in 2, I have divided my flux in 16.
16.
Now that's volumetric flux. We often
So flux being the amount of your fluid that's flowing
volume
through
per time.
Flowing through an area. Gotcha.
Volume per time.
Volume per time. Okay.
That's often flux if it's volumetric flux.
Yeah.
Now, we often normalize it by area.
Yeah.
Right? Because then I have a normalized, so then I just scale by area as I need to. So if I'm dividing by area, that's r square, right? It's r square p here. So then it's gonna, that normalized flux, which is linearized velocity, and that's what we think about as, we often term it as Darcy velocity, because Darcy's law is the first study on that topic. So that's our lens of how fast things go through the ground. So that's not the velocity of like going through all of the pore space. It's kind of like what I see is the front moving through my porous medium.
Yeah. Yeah.
And that's this linearized velocity flux.
Yeah, from what I understand, so you have Darcy's law explaining the kind of macro scale movement of that fluid, but now you have Navier-Stokes that's explaining
so
the
that
grain to
linear
grain.
velocity depends on r square. So that linear velocity will go down by the square of the number that you're reducing the size of your grains.
So the radius of the grain being r.
Now, there is radius of the space in between grains and radius of the grain. They're not the same because I'm not flowing through the grain, but they're very much correlated. So if I have these spheres here, then roughly the smallest spaces in between those spheres are 1/5 of their radius is 1/5 of the radius of the grain, give or take.
Yeah.
There's distribution of sizes, of course, enter geostatistics. There's a distribution of sizes. There's also how they're spatially correlated. But some of the smallest ones are like in that range. That's just a rough number that guides.
Gotcha.
Fun stuff. Let's not go into lecture because we'll be here for hours. You're going to stop me from lecturing. That's a danger of talk.
Cool. Yeah. So, from what I understand, the relationship between porosity and permeability is relatively linear when you have small values of both. But as you get bigger and bigger, it starts to tail off.
Yes.
Could you tell me a little bit about why that is?
So this comes in from the fact that technically, this jar is an excellent, so one place where we actually have pretty good handle on what is the permeability. And for the uninitiated, whenever we model anything, we have a flux of something. And in this case, we're interested in a flux of a fluid. And it could be this volumetric or linearized flux. Often we divide it by area you're going through because that's also how you're collecting things. So that flux is proportional to the gradient of whatever's driving the whole thing. And in fluids is the gradient of pressure. Right? We know that's why our water towers are high up to get the gradient of pressure down to your tap. Right? So basically, and then you have some coefficients in that relationship. Right? So in Darcy's law, you say that this linearized velocity is equal to formally minus K permeability divided by viscosity or resistance of the fluid. More viscous the fluid, harder it is for it to flow.
Yeah, it's like
so in a common
water and honey.
Yes.
Yeah.
So or oil. So oil is gunkier. It kind of resists flow more, so it's less dense. It's going to be on top. But that's
it's more
related to
viscous.
gravity. Gravity, really. But it's more viscous. When I'm starting to flow it in response to the pressure gradient, it's harder to flow.
Yeah.
Right? And honey is one of the. Honey could also be solid, but that's different. Let's not go into talking to honey. I come from honey making family. So I do know my share about honey. And then we have, so basically K over mu times gradient and pressure. That's Darcy's law. And a lot of laws are basically just having that, like I have a couple of coefficients that are relating in a linear way, my flux and my gradient. You could look at a whole other Cook's law has an expression like that. So these linear relationships, Newton's law for viscosity, shear stress is minus mu times gradient of velocities and so forth. So there's always this simple observation of nature. And then we in science do a whole lot of measurements to quantify those numbers so we can be predictive. Now, back to this K, if I actually go and find what K is for a packing of equal spheres, we can go through calculation of that. And it basically comes down to some function of velocity. So I can do it for a bunch of tubes, or I can do it for the space in these spheres. And if you stay with the spheres, that there's a function of porosity in there. So K is equal to, and I trust it's phi squared over 1 minus phi cubed.
I have this written down, so
you have
can double check this.
You have Carmen Coseni? Let's call it just a function of...
Wait, maybe I don't. I have Navier-Stokes and I have Darcy's law written down.
Okay, so in Darcy's law, I'm talking about the expression for K. Okay?
Yeah, it's negative K over mu.
And so that K for sphere packing, which I have here, is given by Carmen Coseni relationship that was worked out in 1920s.
Okay.
By those two fellows separately. And basically, it's a function of porosity times either diameter or radius of those spheres squared, and divided by a factor that we also call 72 times tortuosity. Tortuosity is how geometrically I gotta go do this in a porous medium and traverse a distance that is way more than a straight line.
Oh, so how much
I'm
of
never going a straight line.
How much of a zigzag do you have to move through?
And you can just think about it as the length of your travel divided by the air distance.
Gotcha.
That would be geometrically. But there's this factor that relates to the fact that I'm going through the... So basically, you're formally a function of porosity times r squared. Right? And that's where basically some of this, there's the sizes of the spaces, they're functionally r squared, and then there's function of porosity. So it's both. And because of that, you get this nonlinear behavior. Until you get completely stuck if you have no porosity. Right? So things are valid in certain ranges of all of these values.
Another question I have is that if you were to have a still porous but much, much less porous material, say
So start
maybe
growing cements in these spheres, which is what happened
in
sandstones. Okay.
So you have like an interface between this material, this seems relatively porous to me. It seems very porous.
That's
and you
as
have
porous as it gets in subsurface. Yes. Unless it's a cave, but that's a whole different,
Okay, so I'm going to say very porous material, and then there's an interface here, and then there's much less porous material here. But you theoretically could still have fluid flowing in this direction. But does that fluid tend to favor the porous?
Will go where it's easier.
Gotcha.
So it's going to go through larger spaces, right? And that's what often happens. That's the whole problems we have in subsurface come from that. Yeah. It could come from different layers, and you have layering on all scales. If I take a core that is of this size of a sandstone, you will actually find layers within, and you can often see them with your eyes. And that differentiates different grains that have deposited. Now, visually, I like the visual of Grand Canyon when you have, because that's one of the greatest cross sections that is open to our eyes. Normally, they're not open to our eyes. And you see all of the different reds and what's not. So different layers that have deposited over different times. So all of those different layers have different permeabilities and porosities.
Gotcha.
And they might be sandstones, limestones, whatever they are. If they're down to shale or something that has very fine particles and could be a mixture of clay as well, then that gets really tight.
Yeah.
And yeah, good luck going through those. And those are our cap rocks. They stop.
Interesting.
Entirely. And then you could also, on top of all of that, have fractures.
Yeah.
That intersect all of them. Fractures are highways. So if you have, the problem with fractures though, is that they, in terms of space, don't take these thin slabs, conceptually speaking, and then don't take a lot of volume. So volumetrically, you have 5% of space in fractures, but that's where all of your flow is going.
Because there's nothing interrupting that flow.
Yeah. And you're going to go where it's easier. So if you are trying to produce from those, you're going to just flow through fractures. You produce fractures, and then what? Right? If you try to chase fluids, whatever you inject will go through fractures, and then what? All of the oil sitting in the matrix will be like, see you later. It's like from the windows, right? So in that sense, that's a standard operational problem, because fractures kind of steal most of the flow. They can also cross, so let's say that you fracture this cap rock. That's your leak, and that's a problem. And by injection under, there could be processes that do fracture cap rock. Or there could be certain reactive fluids. So CO2 is quite reactive. If it reacts with the rock, it might damage it and make that fracture more easily.
Yeah. Yeah, I would imagine chemical reactions change the properties.
And that's the game. That's the sort of the area of geomechanics. And this is, again, part of my fascination with subsurface is because all of these things are interesting for different reasons. So there's a little bit of something for everyone to study, right? So pick your fascination. You can find yourself useful.
Disciplinary soup.
Right. It's a disciplinary soup, absolutely. Much more so. Well, a lot of things. I don't think there's anything anymore that is really like a strictly one kind of.
Yeah, I noticed that too. Yeah.
It's 2024.
Right? Yeah. Disciplinary science is gone.
Right. And you can also see that in academic environments. You have in a single department that calls itself Department of whatever, you can have this mix. So a computer scientist could work in all of the engineering departments technically.
Yeah.
So mathematicians apparently can work in a lot of places too. So I'm just saying like that, like one can basically, it's elastic.
Yeah. If we're gonna get philosophical, I feel like
they've been a little philosophical for a while now.
Little sprinkle towards the end here. But I feel like having a fundamental understanding of kind of the mathematics and the physics behind, like you said, like these natural observations, allows you to specialize a lot easier. Yeah. So like you could take the understanding and knowledge of fluid flow through porous rock that you have now and transfer that to, I don't know, biomedical engineering, and you'd probably do just fine. Yeah. And a computer scientist, like Dr. Perch is a great example. Like he could take the data analytics and all of those statistical methods that he uses and use it in
where there's data.
Yeah, where there's data. Exactly.
And a lot of methods that are at the core of all of these things, you do actually learn in math. Now it's data science, but in math and statistics have been, in physics to a large extent, have been like having these algorithms that kind of work in a lot of different. One also that strikes me, graph theory. Everything is a graph to an extent. From we actually work with graphs. We map these pore spaces onto a graph, and you can speed up calculation quite a bit. Especially when you have these fractures that form graph of planes that is intersecting all of these graphs of small stuff. It's actually easier to compute if you give it a giant graph of conduits that have certain sizes to that that you extrapolate from what you know about the subsurface. So you can do a graph and you can flow your fluids through graph. And look, if I map all of the airports back to travel, that's a graph too. Yep. Right? So there is a set of graph theory just works with graphs, whatever they mean to you, right? And you can basically work fundamentally just by knowing graph theory a lot of different problems.
Yeah, that's where
What does that graph mean to you? I could map my lungs as a graph. It's an interesting one because it end up a lot of dead ends, right? But it's a graph, and I can do.
Yeah, that's where the kind of computational competence of AI is really interesting to me, because like you were saying, like you can take, like, it almost maps, just it takes data and then it maps that data into
Yes, neural networks are graphs as well.
Yeah.
Yeah.
And from that you could give it anything and it could tell you correlations.
Different meaning and no fluids flowing through those graphs, right? But those nodes have certain values attached to them.
Exactly.
On how you're passing information through those neural networks. Yes. Yeah. That's fascinating too.
Yeah. So really, yeah, the computational just like
the core level competency comes down to linear algebra, combination of linear algebra, graphs, and differential equations. If you like modeling both physical world, but also differential equations, like financial math, it's all differential equations. We model change through differential equations. That's common use for derivative, right?
Yeah.
And any change, like at the end of the day, what we can measure is always just change, no matter what it is that we're trying to measure.
Yeah. It's a good way to look at it. Yeah.
Derivative.
Derivative of a derivative, of a derivative. Yeah.
Yeah. So we can look at the spatial change or change in time.
Or both.
Or both.
Yeah.
From the math standpoint, that's just your choice of variables, sir. So that's you can call it whatever you want to call it.
So on the topic of AI, I'm really curious about. So I remember watching one of your online lectures, and you talked about.
I use it too, yes.
You talked about how there's an inherent bias in one institution or one company using AI with only their data.
Yeah.
Could you talk a little bit about that?
How do we use AI? Or machine learning, deep learning, whatever umbrella of learning, is that I'm learning from data and what is data telling me. And the simplest form of that has been around forever, linear regression. Remember that topic in 311? We have history here, lecture 7 in the course I taught last summer. But basically, what I'm trying to do is strike a line of how is my cloud of data points in 2 dimensions behaving. And that line is a functional relationship. Back to linear relationship is always the first one we go to.
Yeah.
My Darcy's law is a linear relationship of sorts too. So basically I'm trying to figure out, hey, give me X, I'll give you Y. We want to predict. Now, neural networks do that too, in a much more sophisticated fashion, but at the end of the day, they're just trying to extract relationship. I'm just not going to write it down as a function. I will actually pass my information as input on one end through the network, and my network, neural network, in the course of training with the data, has figured out which coefficients to place where based on the data it saw. And then when I pass my new data set through that network, I'm going to get a prediction on the other end. Right? So it's not a function anymore. It's a form of a function. And it's a little bit harder to interrogate what's in there. Right? So now if I'm whatever company or whoever it is that I am, I'm doing certain type of research, right? And I'm doing it in a certain way with certain tools. And that's my data that I'm feeding this network. If I learn only from that, I have learned from the experience of Maša Prodanović, if it's in porous media. But that's a very limited experience. I have focused on studying certain types of problems, flows, and so forth, right? In my limited time, that's the best I can do. Right? And somebody else has more and different experience, and we should actually learn from all of the experiences.
Yeah.
And it translates to anything. It doesn't matter what I do. Right? So in that sense, we need to learn from multiple and learn to extrapolate from a larger set that encompasses all of the possibilities.
Yeah. Right? Beautiful point. I like
so,
that.
but there was an example, the stuff with ImageNet, was it? And
I'm not familiar.
so if you go to imagery and learning from imagery and learning to recognize faces.
Oh, is that okay? Yes, I am familiar. I'm sorry.
In the library that was created was predominantly white. And then it couldn't recognize people of color. Well, bad data set.
Yep.
Again, all of these methods, they're just extrapolating from what they saw. Right?
Yeah, my research supervisor describes AI as like it outputs what you give it. So if you get if you put garbage in, you're gonna get garbage out. Yeah.
And one of the so I've worked in this predicting velocity field in this same context that I've been talking about. So I actually do sit with Digital Rocks portal that we haven't introduced yet, but basically there's a whole lot of images of porous media out there. I'd like to learn from them, and I tend to curate those in the form of a portal. So we were actually doing research where we are extrapolating velocity and permeability from those same data sets. Now, if I do that, I don't do it as a finite. I want it to enhance fluid flow is relatively common, and it's a baseline of what I need to know in porous media. But things that are actually interesting to me are coupled processes. So I have flow of fluid, and maybe there are some particulates within. Or my fluid is a very complex one, like foam. So the bubbles of foam keep like moving through, splitting and reforming and changing as they go through. And that type of phenomena we can even barely simulate. So a lot of people in my research group work on like, hey, can I simulate what happens when I produce foam in a porous medium? But I don't need AI for that. But AI could speed up giving me that velocity field so I can that quicker. So I don't think AI can just magically now give me, hey, here is your velocity field for your foam. No, it hasn't been trained on foam. It hasn't seen foam yet. Right? But it can help me get to the simulation of foam faster. Gotcha. So we need to not lose sight. Yes, AI can do a lot of things, but at the same time, it's just extrapolating what we've seen, and we have to be mindful of that. And as such, it can speed us up, but we need, as people, we need to learn to keep our knowledge of what all is happening and our openness that there might be something we haven't seen and haven't studied. And I think that's one thing where we need to, as a culture in 2024, be really careful with AI, not to become too comfortable with all of the predictions it's giving us. Right? Learn to stay uncomfortable and ask yourself what it is that I don't know. Is this really a true answer? Just because computer gave it to me.
Yeah.
So, but just because it's easy.
I think that's a great note to end on. We're all out of time today, but thank you so much for coming on the show. I really, really appreciate it. And I want to give you a couple minutes at the end here to promote anything that you have going on. What's the new research?
So bad at it.
Where can people contact you?
I'm a poor excuse for a marketing person. That is certainly not the career I should have. Well, okay, so I'll mention. So I do work on Digital Works portal is one thing that I'm developing where I'm collecting a lot of data sets that I'd like to learn on, learn from. Right now, what we're working on is like new things that 1 year ago 2 years ago, maybe I wasn't thinking too much about it, or maybe I just started. But as I'm collecting data, and yes, I want to learn from the data, from I'm also thinking that I don't want to collect all of the possible data people could give me. So data also has to stay at the origin. So how do we actually do learning when my data is sitting in multiple locations? It's actually called federated learning. So we're looking into that, and basically then question is, if I don't see the data in that other place, I don't want to move it to me, it's too much, or maybe there's some data privacy issues, so that other company doesn't want me to put my fingers on the data, but can I actually just send my model to learn there and come back? But then I need to have a data quality check on that data, and that's an outstanding problem. Like, if I see an image, is it a good data set to work with without seeing the image? What are the numbers I need to go through? So that's some of the directions we're going through, and also always developing new simulators that simulate various fun fluids, and what do they do as they go through porous media. So everybody's very welcome to check Digital Rocks portal. I do have a YouTube channel. Since the pandemic, I haven't posted much lectures. I was one of those people posting my lectures before pandemic.
Ahead of the curve. Yeah.
And then now I still record all of it. So I would basically just record what I do. You can find a set it was called 310 then, from 2019. It's sitting on my YouTube channel, because I would basically record what I'm saying over my slides as in coding and whatnot. And that now moved on Zoom, and now there's actually clear restrictions in FERPA, because I could also potentially record a student along the way.
Yeah.
So that I kind of stopped that practice, just simply got interrupted by pandemic. But here and there I will still have like a lecture on something or a presentation related to the data on Digital Rocks portal.
Yeah.
So, not very active. Certainly not as active as Dr. Purchase in that space.
I think there are a few who are as active as Dr. Purchase with that stuff.
Right. It's amazing that he does that, and but it's amazing amount of time.
Yeah.
And some of it is like where I am in my personal life. I have a little bit less. My children are taking some time. So
as they tend to do.
As they tend to do. It's
Yeah.
wonderful, but then there's a little bit of less. I have to be a little bit more careful about my time. So that's why I'm not investing. But give me 5 to 10 years, I'll come back. So.
All right, well, you heard it here, guys. Possible Maša Prodanović YouTube revival in 5 to 10 years.
Right.
Yeah.
So.
But yeah, thanks for coming on. I look forward to seeing what you and your group do next. And yeah, thank you.
Thank you very much for having me.
Yeah.
And enjoy your little
Thank
reservoir.
you.